Hello everyone, I'm Kamel Ghali, Professor of Mechanical Engineering at the American University of Beirut, and today I will be presenting my work on novel concept of autonomous liquid desiccant-based system for sustainable indoor humidity pumping. I will start by presenting the motives and incentives behind this study and the objectives of the work. The system configuration is then presented with the methodology that is adopted to evaluate the system performance along with the sizing strategy. This is followed by a case study to which the proposed methodology is applied. Then I will present the result depicting the system performance, a conclusion, and future work. Many literature work highlighted the need to provide hydrothermal comfort in the aim of protecting the building structure and people health and well-being. In fact, high levels of indoor moisture leads to mold growth, causing asthmatic reactions to the occupants. In addition, high indoor relative humidity hinders the body's ability to dissipate heat by transpiration, affecting thus the occupant perceived thermal comfort. The moisture concentration level in indoor spaces has been moderated by the use of HVAC system. Conventionally, this system could control the relative humidity levels by supplying outdoor air that is dehumidified and cooled using mechanical air conditioning system, either as standalone devices or integrated with desiccant system. However, for condensely occupied spaces in extreme hot and humid climates, these systems are energy intensive due to high electric power consumption of the electric compressor and the high thermal regeneration energy of the desiccant systems. So it is becoming important to seek energy efficient and cost-effective solutions to sustainably reduce the indoor humidity at reduced energy cost. The solution is thus to pump moisture from indoor air towards the outdoor instead of diluting it with a supply of dehumidified air. However, this concept is not well matured, and many limitations were found in the previously adopted methods, such as active regeneration and cooling for effective operation required for liquid desiccant system, and the intermittent operation with complex switching mechanism and low capacities of material faced by solid desiccant systems. Therefore, there is a need for a sustainable humidity pump with autonomous and continuous operation. How can we achieve this? A highly hygroscopic liquid desiccant is proposed to circulate in a semi-permeable membrane-based Thermosyphon loop with breathable insulation layer on the room side. What are the advantages of this system? It provides easy control of indoor humidity levels through direct removal of humidity. It eliminates the need for the pump and parasitic power consumption, and it eliminates the need for cooling the solution using the insulation. It can benefit from solar radiation directly to drive the Thermosyphon flow. So the aim of this work is to assess the feasibility of the proposed system to passively pump the indoor generated humidity to the outdoor environment through a case study of a space with high moisture generation rate at different outdoor humidity conditions, and to determine the pumped latent load and added sensible load to the space when the system is operated at different heat inputs to the solution and the resulting coefficients of performance. This work considers an occupied space with high internal latent load. The space has a facade exposed to the outdoor environment and provided with mixing air conditioning system that supplies cool outdoor air to regulate the space temperature within the comfort ranges, as well as to provide acceptable indoor air quality. The passive humidity is incorporated within the external wall section to pump the indoor air humidity towards the outdoor environment. The humidity pump is formed of three components: a liquid desiccant loop, a storage tank, and a breathable insulation layer. The system operation is as follows. The solution tank is heated to circulate the liquid desiccant. in the membrane via buoyant forces. In the outdoor side of the membrane loop, the water vapor pressure level increases beyond that of the outdoor. This effectively regenerates the desiccant solution, which is then collected in a metallic header to prevent water moisture transfer with the environment. The header is fanned to enhance the cooling of the solution with the outdoor air. The warm solution enters thus the loop inner side to absorb the moisture from the room air before returning to the tank. The inner insulation facilitates the diffusion of the indoor air moisture towards the liquid desiccant solution while creating a barrier to the heat coming from the warm solution. Note that the storage tank is used to avoid fluctuations in the system operation by stabilizing the solution concentration. The performance of the system depends on the effectiveness of the absorption-desorption phases in the desiccant loop. Validated mathematical models are developed for the heat and mass transfer of the sorption process. The terms of the solution mass balance equation represent the water storage in the liquid desiccant solution, the effective mass flux, and the mass flux entrained from the indoor air by diffusion from the membrane and insulation layers, respectively. The terms of the solution energy balance equation represent the heat storage in the solution, the effective heat flux, the convective heat transfer with the room air, and the heat gain lost due to absorption-desorption of water vapor. Note that the solution flow rate, MDOT solution, is determined from the analytical Thermosyphon model. A space model is needed to predict the indoor air conditions of temperature and water vapor content. This model requires as input the building geometry, orientation, and envelope material, as well as its occupancy schedule and the generation rate of water vapor to solve for the temporal variation of the indoor air conditions as a function of those of supply air. The proper sizing of the different components of the proposed system is vital for its efficient operation. For the membrane loop, there are geometric constraints imposed on the inner side. The available area for the moisture transfer is limited between 30 to 50% of the wall area. The channel height should not cause excessive decrease in the solution concentration. The channel gap is set to impose a velocity between 1 and 2 meters per second for effective mass transfer. For the outer side of the loop, the same width is maintained, however, with a different height, which is set to ensure complete regeneration of the desiccant solution. The thickness of the insulation layer is determined based on the available material in the market, with the consideration of reducing the sensible gain to the space without excessive increase in the water vapor flow. The validated model is applied for a case study of a typical space with a fixed high indoor moisture generation rate. To assess the system performance, 3 representative weather conditions are considered: hot and humid at 35 degrees and 70% relative humidity. This is referred to as high relative humidity case. Hot and moderate humidity at 35 degrees and 50% relative humidity. This is referred to as moderate relative humidity case. And hot and dry, 35 degrees and 30% relative humidity, referred to as low relative humidity case. This is important to study the proposed humidity pump performance under all possible outdoor humidity conditions to determine the limitation and applicability ranges. The most suitable liquid sorbent membrane and breathable insulation must be selected to have complementing characteristics and ensure the effective performance of the humidity pump. Potassium formate is the adopted liquid desiccant, which is a weak acid that have recently gained attention. It showed a considerable low generation temperature between 45 to 55 degrees Celsius with a lower viscosity compared to conventional adsorbents. Such low viscosity is crucial to reduce the required pumping power and enable the buoyant forces to create the needed solution flow rate to ensure effective operation of the system, a typical concentration of 75% for the potassium formate solution is considered in this study. As for the membrane material, the commonly used PVDF polymeric membrane is used, which is a selective hydrophobic porous layer permeable to water vapor but impermeable to the liquid solution to prevent any carryover. Furthermore, mineral wool is used as a highly breathable insulation layer due to its low thermal conductivity and high water vapor permeability. The different developed models were first validated with published experimental data. The space model was validated against a calibrated Francis model and showed a discrepancy of plus or minus 5% on the prescribed space temperature. The adopted absorption model was validated experimentally, and the maximum error on the predicted outlet air temperature, humidity, and desiccant temperature were 1 to 1.1%, 1.6%, and 0.9% respectively. The analytical solution of the Thermosyphon was validated with published experimental data and used in the applicability range of temperature and heat input. The proposed system was properly sized and simulated for the 3 different outdoor humidity conditions. The sizing approach was thus applied for the case study, and an area of 1.8 meter times 2.7 meter was needed with a channel height and a gap of 1.8 meter and 4 centimeter respectively for both inner and outer loops. Furthermore, a typical insulation thickness of 50 millimeter was selected for the mineral wool layer. The size system was then simulated for the 3 different cases of outdoor humidity, and the results are presented in the next coming slides. For the low humidity case, the removed latent heat from the space increased with the heat input to the tank until Q latent reached a maximum of 8 kilowatt. This is due to the increase in the circulated mass flow rate with heat input. However, as further heat was supplied to the solution, the pump latent heat decreased due to 2 main reasons. The decrease in the solution flow rate, since the cooling side of the loop is limited to the high outdoor air temperature, and the fan's effectiveness. Second, the increase in the inlet solution temperature to the room side of the loop increased its equivalent vapor pressure, which reduced the driving gradient for the moisture transfer from the room to the solution. Similar trend was obtained for the cases of moderate and high relative humidity. However, with lower removed latent loads. This is due to the reduction in the ability of the solution to be fully regenerated on the outer side of the loop, caused by the reduced gradient of the water vapor between the solution and the outdoor air. Note that for high relative humidity case, the minimum heat input needed to operate the proposed system was 5 kilowatt in order to provide the high regeneration temperature required to overcome the high outdoor water vapor pressure. Here we present the coefficient of performance of the system, which is the ratio of the removed latent load over the latent heat input to the solution. The resulting COP of the system decreased with the increase in the outdoor relative humidity and presented a maximum value for a specific heat input to the tank. A COP of 1.54 was reached at low relative humidity for a heat input of 5.2 kilowatt. At the moderate relative humidity, a maximum COP of 1.13 was reached for a heat input of 6.5 kilowatt, while for a high relative humidity, a heat input of 7 kilowatt was needed to attain the maximum COP of 0.75. Note that a rising shift in the needed heat input was observed with increased outdoor humidity levels. Finally, it was noted that sensible load is the same for the different outdoor relative humidity levels. This is expected since Q sensible mainly depends on the heat input supplied to the solution and the subsequent increase in the solution temperature rather than the humidity levels. This work proposed a sustainable humidity pump that uses liquid desiccant driven by a thermosyphon loop. A sizing approach was developed and applied for a case study considering 3 different outdoor humidity conditions. The system was simulated for a different heat inputs to determine the optimal operating condition. It was found that the system performance was affected by the outdoor relative humidity levels. The maximum COP decreased with the increase in the humidity. A high heat input was needed to operate the system at higher outdoor relative humidity for the same latent load removed. The system performance can be enhanced by optimizing the different subcomponents design, especially the pre-civil insulation, to reduce the sensible heat gain without retarding moisture flow. Moreover, the membrane performance can be improved through the impregnation of adsorption materials such as metal organic framework to reduce its water vapor diffusion resistance and provide it with adsorption properties. These are the references for the presentation and the work. And finally, I like to acknowledge the support of the Maroon Sam'an Faculty of Engineering and Architecture Research Initiative. Thank you.